Good day everyone. Welcome to Marine Engineering Mathematics. Today we dive into linear and simultaneous equations. Don't let the math terms intimidate you. By the end of this session, you'll see that these equations are simply powerful tools that we use in daily shipboard operations to balance our machinery, track fuel, and plan a safe voyage. Let's look at what we want to achieve today. First, we'll understand algebra using a simple visual, a traditional balancing scale. Our goal is to learn how to get an unknown variable, like x, completely by itself so that we can solve it. Secondly, we'll look at how equations form straight lines on a graph and what that means. Finally, we'll learn how to take two different mathematical clues together using methods called substitution and elimination to find one perfect solution where those clues meet. We'll begin with linear equations. Think of this as the absolute bedrock of algebra. It's all about understanding the fundamentals of balance and finding the value of a single hidden variable. Think of an equation as a traditional mechanical balancing scale. The equal sign means both sides weigh exactly the same. Therefore, the golden rule of algebra is simple. Whatever you do to one side, whether you add, subtract, multiply, or divide, you must do exactly the same thing to the other side to keep the system in perfect equilibrium. Our ultimate goal is to isolate our unknown variable, usually called x, completely on one side, so it reveals its hidden value. Equations aren't just numbers on paper, they form pictures. The standard equation for a straight line on a graph is y is equal to m times x plus c. Let's break that down simply. Y is our result or dependent variable. X is our independent input. M is the slope, which just tells us how steep the line climbs or falls. And C is the intercept, the exact baseline starting point where our line crosses the vertical axis before X even starts changing. Here is what that looks like visually. Notice how the blue line starts at 10 on the vertical y-axis. That's our C value, or y-intercept. As we move across, the line climbs steadily at a rate of 5 units for every step we take forward. That steady climb is our slope, m. Geometrically, a linear equation draws a line that stretches out infinitely in both directions on a two-dimensional grid. Every single coordinate point, xy, that sits exactly on that blue line is a correct solution to the equation. Because a solid line is made of an infinite number of points, a single linear equation actually has an infinite number of solutions. Two key points to remember are the x-intercept, where the line crosses the horizontal floor axis, and the y-intercept, where it crosses the vertical wall axis. Let's practice solving a single equation using our balancing scale logic. 2x plus 5 is equal to 10. Remember, we want x by itself. Step 1. Get rid of the trailing plus 5. by subtracting 5 from both sides, leaving us with 2x equal to 5. Step 2. 2x means 2 multiplied by x. To undo multiplication, we divide both sides by 2. This completely isolates x, giving us an answer of 5 over 2 or 2.5. Simple balance steps. Now let's step it up to simultaneous equations. This sounds fancy, but it just means solving multivariable situations where we have two unknown values, but we are given two distinct mathematical clues to solve them together. Imagine you have one equation. As we learned, it draws a line with infinite possible answers. But what if we introduce a second independent equation? It draws a completely different line across the same grid. Solving equations simultaneously simply means looking for the exact rendezvous point where those two lines cross each other. That single intersection coordinate xy is the only point in the universe where both mathematical clues are perfectly true at the same time. While graphing lines is highly visual, drawing grids in the middle of a busy engine room isn't always practical. Instead, we use two reliable algebraic methods to find that intersection point. Method A is substitution and method B is elimination. Let's look at how they work. The substitution method is your best strategy when one of your equations already has a variable isolated on its own. For example, if a clue tells you flat out that y is equal to 2x, you simply take that known equivalent and plug it directly into the other equation. This magic trick transforms a confusing two-variable problem into a simple single-variable problem that we already know how to solve. The elimination method is ideal when your equations are neatly stacked vertically in standard form. Think of it like adding or subtracting entire equations together like standard columns. By adding or subtracting the lines, we intentionally force one of the variables to completely drop out or be eliminated. This allows us to easily solve for the surviving variable, and then we just circle back to find the first one. So how do you know which tool to pull from your math toolkit? Use this simple cheat sheet. If one variable is already isolated, use substitution. It's straight plug and play math. If the equations are neatly stacked with variables on one side and a total on the other, use elimination to cancel a variable out. Watch out for fractions in substitution, and remember, you might need to multiply a row first in elimination to match things up. Before we look at real ship examples, let's look at three common traps. First, the negative sign slip. Be incredibly careful with your minus signs, as forgetting that subtracting a negative equals an addition is the number one error in algebra. Second, stopping halfway. Finding x is only half the journey. You must plug it back in to find y. Finally, skipping the verification. Always take 10 seconds to check your answers in both equations to guarantee you are 100% correct. Let's sharpen our tools with these three starter problems. Problem 1 is a warm-up to isolate x. Problem 2 is perfectly set up for the substitution method because x is already isolated. Problem 3 is a stacked equation layout requiring the elimination method. Take a moment to try them out. Here are the solutions to confirm your work. For the warm-up, x is equal to 3. For the substitution problem, the intersection point is at x equal 4 and y equal 2. And for the elimination problem, our coordinates are x equal to 8 and y is equal to 4. If you got these right, you've officially mastered the core mechanics. Now let's talk about why we are actually here. In marine operations, a linear equation represents a real-world straight-line relationship where a change in one factor causes a predictable proportional change in another. On a ship, we use these exact linear relationships daily to track fuel consumption, predict tank levels, and catch machinery failures before they happen. Let's look at question 1. Imagine our auxiliary generator burns fuel at a constant rate of 0.25 metric tons per hour. However, because of pump suction limits, the day tank has an unpumpable deadweight baseline of 1.5 metric tons that we cannot touch. If we are planning a 48-hour voyage, how much total fuel must we account for? Step 1. We write our linear equation. Fuel is equal to 0.25 times hours plus 1.5. Step 2. We plug in our 48 hours. Step 3. 0.25 times 48 is equal to 12 plus our 1.5 baseline buffer gives us a total requirement of 13.5 metric tons. Let's look at that exact fuel problem mapped out against our standard y is equal to mx plus c line formula. Our total fuel F is our dependent result y. A constant burn rate of 0.25 is our slope m. The 48 hours steamed is our changing input x. And that untouchable baseline fuel buffer of 1.5 is our constant intercept c. Let's look at another critical fluid, main engine cylinder lubricating oil. These systems inject expensive oil at a rate based on engine speed. As engineers, we use linear equations to calculate exactly how much oil a voyage should take. If our actual tank level drops significantly faster than our linear formula predicts, we instantly know we have a mechanical leak or a calibration error in the lubricator clocks. Here is our second scenario. A container vessel's main engine consumes cylinder oil at a constant rate of 15 liters per hour while cruising. The service tank requires a baseline buffer level of 200 liters to maintain proper pump suction and prevent dangerous airlocks. If the bridge team estimates a transit time of 72 hours between ports, what is the minimum oil requirement we must have in that tank before departure? Let's build our equation. Total volume V equals our consumption rate of 15 multiplied by C hours H plus our 200 liter safety buffer V equal 15H plus 200. Plugging in our 72 hours transit time, we get 15 times 72, which is 1080 liters of operational consumption. Add the 200 liter suction buffer and we find we need a minimum of 1,280 liters in the tank before departure to complete the voyage safely. Next up, fresh water generation. Making fresh water via waste heat evaporators is critical for ship boilers and crew accommodation. These systems produce fresh water at a steady rate depending on engine load. We track this linearly to ensure we don't run dry or overflow our holding tanks. Let's look at question 3. Our waste heat freshwater generator produces 1.2 metric tons of fresh water every hour. At the start of your 12-hour watch, you sound the domestic tanks and find they already contain 45 metric tons of water. If you run the evaporator continuously during your shift, what should the predicted tank level be when you hand over the watch? Using our linear line formula, we write total water, W, equals our production rate of 1.2 multiplied by the running hours, T, plus our initial 45 metric tons starting level. W is equal to 1.2 times T plus 45. For a 12-hour watch, 1.2 times 12 is equal to 14.4 metric tons of new water produced. Adding our 45-ton starting point, the tank should read exactly 59.4 metric tons at the end of the shift. If your physical measurement is lower than this math, you instantly know your heat exchanger plates are scaling up and losing efficiency. Now let's apply simultaneous equations. For marine engineers, these are essential for balancing interconnected systems and optimizing constraints, like managing your speed versus your total fuel limitations. Suppose a ship has to complete a transit with two different operational profiles, a high-speed sprint to beat an oncoming storm, and an eco-speed cruise to save fuel. The chief engineer allocates exactly 24 hours total for the transit, and the bridge needs to know exactly how many hours to run at sprint speed, X, versus eco speed, Y, to make it work. Here are our two strict constraints. First, our total time is exactly 24 hours. Second, our maximum fuel budget allocated for this leg is 54 metric tons. Our consumption logs show that at sprint speed, we burn a heavy 3 metric tons per hour, while at eco speed, we burn only 1.5 metric tons per hour. This gives us two distinct equations. Our time equation, x plus y is equal to 24, and our fuel equation, 3 times x plus 1.5 y is equal to 54. Because these are interconnected constraints, we use the substitution method. Step 1. Rearrange our time equation to isolate y, giving us y is equal to 24 minus x. Step 2. Substitute this expression into our fuel equation. Step 3. Expand and simplify the math down to 1.5 times x plus 36 is equal to 54. Step 4. Solving for x gives us exactly 12 hours of sprinting. Step 5. Subtract 12 from our 24-hour total, and we get 12 hours of eco speed. To maximize our distance safely within the fuel budget, the ship must run exactly 12 hours at sprint speed and 12 hours at eco speed. Our final scenario involves a regulatory inspection. A class surveyor wants to verify the individual full capacities of two parallel connected centrifugal pumps, the bilge pump, pump A, and the ballast pump, pump B. The individual flow meters are broken, but the main manifold flow meter works fine. We can run tests by throttling the pumps to half capacity to create our stacked mathematical clues. Here's the data from our standard test configurations. Test 1. Running pump A at full capacity A and throttling pump B to half capacity 0.5 B yields a combined flow of 130 cubic meters per hour. Test 2. Running pump A at half capacity 0.5 A and running pump B at full capacity B yields a combined flow of 140 cubic meters per hour. How do we find the true full capacity of each individual pump? Because these equations are neatly stacked, we use the elimination method. Step 1. Align our two test equations. Step 2. Multiply the entire second equation by -2 so that the B coefficients become opposites, giving us -A minus 2B is equal to minus 280. Step 3. Add this new equation to our first equation. The A terms completely cancel out, leaving us with minus 1.5B is equal to minus 150. Step 4. Solve for B, which proves pump B's full capacity is 100 cubic meters per hour. Step 5. Plug 100 back into our first test and we solve for A, showing pump A's full capacity is 80 cubic meters per hour. Both pumps are verified and fully compliant with regulatory drawdown limits. Let's summarize the key takeaways of what we covered today. Linear equations, y is equal to mx plus c, allow us to track fuel, oil, and water levels, giving us predictive maintenance capabilities to spot leaks or scaling. The substitution method helps us optimize range planning and transit profiles to maximize distance within strict fuel limits. And the elimination method lets us verify parallel machinery capabilities to prove regulatory compliance. Math isn't just an abstract academic exercise. It is a vital toolkit that keeps our ship running efficiently and safely. Thank you for your time, and I hope that you benefited from this lesson.